to speak today. So like Myra said, I'm going to tell you a little bit about this project, the cyclic homology of categorical coalgebras and the free loop space. This is the bulk of my thesis project, which I'm wrapping up as well as my degree here at Purdue. Right. So first, a little bit of motivation. So the point of this project was to construct or deal with a tractable model for the equivalent homology of the free loop space of a possibly non-simply connected space, which is a mouthful, but hopefully as we go along that these like this sentence will make sense. And then this would, amongst other things, unlock some computations in string topology. Now, the main tools that we use for this project are cyclic homology theory. So cyclic homology theory is a homology theory that was developed for algebras and coalgebras. Right, and it has many generalizations, but initially it's a type of homology theory that was developed for algebras. Another thing that we'll see heavily today is causal duality. So causal duality relates algebras and coalgebras, and the manifestation that we'll be seeing is this bar-covar adjunction. And then the one version of it looks like this. There's a covar functor that takes conilpotent DG coalgebras over some ground ring R, which we're going to fix for the talk. Let's just assume that's a nice ring R. And then this spits out a differential graded algebra with an augmentation over R. And then it has a right adjoint, which is bar. So if you don't know what covar and bar are, it's really not that important for today, but the point is that there's an adjunction between the special kind of coalgebra and algebras. And as we go along, we'll see that some combinatorics like naturally arise when we think about these type of questions. These chain models for spaces and for loop spaces. And then what really this means today is that will be lots of pictures today. Which is a good thing if you like pictures, and not a great thing if you really like formulas and precise statements in mathematics. So right. So first, let me introduce the co-Hochschild model for the free loop space. So let's say before we start, let me tell you a bit of where we're going towards. Given X a topological space, I can associate to it I can construct its free loop space of loops on X with a compact open topology, and that's also a topological space, and it's of interest to study the topology of this new space, loops on X. Alternatively, I can think about the chains, the singular chains on my space X, and then I can. So what we're going to try to do is construct loops out of this object, right? This is an algebraic object, so we're going to try to model this passage from X to its free loop space by some passage here from the chains on X to something, and that something is going to be the co-Hochschild complex. Okay, so let me start. We start with X, a topological space. We can construct its chain complex of singular chains. This chain complex is also a coalgebra, so it has the additional structure of a coalgebra. So just as a reminder, an algebra is some object that has a notion of multiplication. So two elements produce a third element. A coalgebra has a dual notion, which is a coproduct. So given an element on my coalgebra, I should be able to produce an element here. And then the way that I'm thinking about this coproduct in general is kind of like I have an element in my coalgebra and kind of like split it up and get these two elements, right? a little bit more concretely, for the coalgebra of singular chains, the coproduct is given by the Alexander-Whitney coproduct. So in pictures, again, this is not very precise, but in pictures, just to give an illustration of what I mean, if we think of this triangle right here as a two chain on X, right? So a triangle on X, then the coproduct on this should kind of like give me all the ways that I can split up this triangle on X into synthesis on X, right? So one option would be to, I take the first vertex, also the leftmost vertex of my triangle, and then I put the rest of the triangle on the right. I can do the opposite thing, get all of my triangle and then put the last vertex on the right, or I can split it up like this, right, where these are the edges, they're not the bottom edge. Right, so different ways of splitting up my triangle while having a degree 0 map. Okay. Now, since I said that I wanted to use causal duality, and causal duality takes as input, or the covariant functor that fits into causal duality takes as input a very specific flavor of coalgebra, which is a conipotent coalgebra. The coalgebra of singular chains is not conipotent in general. So in order to fit into the framework of causal duality, we have to consider a different version of these singular chains. To do so, one option to make it fit into the framework is to choose a base point. So if we choose a base point in X, and then we consider the singular chains that are based at that point, so every single vertex goes to a single point B, then we actually get a connected coalgebra, which is actually in particular a conipotent coalgebra. Connected just means that on degree 0, we have one copy of the ground ring, right? Which this is representing the choice of base point, right? So that's going to be our vertices. Since we only have one, then we have one copy of the ground ring. Okay, great. And then after we choose a base point and we make this fit into the framework of causal duality, we get some nice results. So for example, we're going to get this theorem. So let C be a connected PG coalgebra. We could also say conipotent, but since I care about connected right now, I'll just say connected. And then we have this quasi-isomorphism of chain complexes. So on the left, we have the coaxial complex of the coalgebra C. And on the right, I have the coaxial complex of the differential graded algebra cobar C. Right? And then hopefully you could see that probably behind this lies the causal duality relationship, because we're using the cobar functor and so on. Okay, so I have not told you what coaxial and hoxial are. They are kind of like, in a way, dual constructions. I will try to describe the coaxial construction in a little bit more precisely right now, and I will not really describe the hoxial construction in general. Hopefully you'll trust that it's a dual construction that's kind of like similar. We only use the ingredients that we have on the algebra side rather than the coalgebra side. Okay, so what is the coaxial complex of a coalgebra C? Well, it's this infinite direct sum of things that look like this. So what is that? Well, we have one copy of C, and then we tensor with n many copies of the positive part of C, and then we shift it down, right? So we basically discard the C0 part, the degree 0 part of C, and then we shift everything down. And then the elements in the coaxial complex are going to be sums of things that live in one of these, which we think as like monomials, right? They're monomials where one term is it lives in C and one lives in the shifted down version of C. Okay, and then we can define on it a differential that we're noting by partial, which uses both the differential of the coalgebra C and the coproduct of the coalgebra C, right? So this means applying each component-wise on each element of the monomial. Okay, again, this is still a pretty algebraic, probably confusing description if you have not seen the coaxial complex or the axial complex before. So I'm going to try to give you a kind of like heuristic way of thinking about elements in coaxial, or at least how I think of them. So I like to think of elements in coaxial as loops in a coalgebra. So what do I mean by that? Well, let's choose an element on one of these pieces of the coaxial complex. How does it look like? Well, I'm going to denote it by these symbols, but I'm only using this notation to say that, you know, we have a special copy, a special element C0 that lives outside in C, and then we have a bunch of C1 through Cn that are shifted down, and they're not allowed to be degrees here. And then the grading that we have is the grading given by the tensor product, which is just, we're going to add up all of the degrees of this thing, right? But now C0, you know, has its own degree, but for each degree from C1 to Cn, since we shifted it, you know, we shifted everything down, we're going to get a -1 from, you know, for each of them, right? So we're going to get the sum of all the degrees before the shift minus the length of the monomial, let's call it. All right. So what do I mean by loops in a coalgebra? Well, what I mean is, let's say for n equals 2, just to draw something. So we'll have an element like that. Well, I'm going to think of this as arranging my coalgebra elements in a circle, C0, C1, and C2, and one of them is special. So that's why I'm thinking about this thing. So an element in coaxial in my head looks like this. And what does the differential do here? Well, this should be all the ways that I can apply, you know, for example, D of the coalgebra here on C0, and then the other ones stay the same. And then all the ways that I can apply D around my circle of elements of C. Right, notice that this indeed will decrease the degree by 1, but there's another way of decreasing the degree by 1, which is making n larger, which means making this list longer, right? And how can we do that? Well, we can use the coproduct, right? We'll split up one element into 2, and that makes our, you know, circular arrangement of elements of C having one more element, and then that's exactly what we do. So let's say that here in C0, we choose to apply the coproduct to C2 to C2. And it turns out that defining this like that gives us an honest differential, and we get a chain complex, and that's the coaxial complex.
Daniel,
okay, so,
can I interrupt with a question?
Yeah.
So if you can apply the differential or the coalgebra structure in any of the points, what's the meaning of choosing like C0 to be special here?
Right. You're gonna have you want a special, okay. The meaning is the following. So at least in my head, what we're trying to do is we're trying to mimic building loops on X. Right? We're trying to mimic building loops on X, and loops on X are a map from S1 to X. Maps from S1 to X have a special point, right? Which is, I mean, depends on how do you wanna, you know, how do we want to think about this? Let's think about, you know, a loop as a map from 0 t to x, such that you know, make the sigma, such that sigma 0 equals sigma t, right? A map like this has a special point, which is exactly the image here, right? And then when I mark my loops here, I'm thinking of it as choosing a special point there. So I guess that my answer is not satisfactory in the algebra sense, but maybe it suffices hopefully because I want to use it to model these type of maps. So I want to single out a special point.
I see. And then after you apply the differential, would you single out like the same location of the points?
Yeah, exactly. So when so here I single out this one, here I single out this one, and I have to be careful when I split up C0, right? Because if I split up C0, I have two options. Let's say that this is C0 prime, and then this is C0 double prime, images of the coproduct. Now I have a choice, and I have to consider both. So I either color that one, or I color this one.
Oh, I
and I'm
see.
going, yeah.
Each of
And I'm
the colorings you would consider as a distinct loop
correct.
here. Okay,
Correct.
gotcha.
Yeah.
All right,
Yeah.
thank you.
Yeah, you're welcome. Thanks for the question. Okay, now if we use as input for this Kohashu complex the coalgebra of base singular chains, then the work of, so this is work of Jones and Goodwillie and others, and then is, I would say, mostly like around the 80s. Then this is related to, this is not just related, this is quasi-isomorphic to the chains on the free loop space of X. Okay, right, which is nice in the sense that, you know, it's showing that I can either have X and build loops out of it, or I can have an algebraic model for X and build loops out of the coalgebra, right, out of the algebraic thing using Kohashu. Right? And I get like essentially the same information topologically. Okay. So these are some results from the 80s. Now, there's something here that is not entirely satisfactory, which is that on the right-hand side, when we look at the free loop space, to study the free loop space, we need not choose a base point, right? There's no need to choose a base point. However, on the left, we are choosing a base point. And that's how we make it fit into the causal duality framework. So this kind of suggests that there should be another framework, another algebraic framework that we could use, in which we do not choose a base point, and we're allowed to work with many points. And then, fortunately, there's a version of causal duality, so a version of the Kovar functor that takes a many-object version of a coalgebra and maps it into a many-object version of an algebra, right? This is work of Holstein and Lazarev. They call it categorical causal duality. And then they describe it as a version of Kovar. I mean, the whole adjunction passes, right? But like, there's a version of Kovar that takes in categorical coalgebras, and it gives you DG categories. So perhaps you've seen before that DG categories can be thought of as many object version of DG algebras. And in the same spirit, we can do the same for categorical coalgebras. Now, again, since in this talk I really care more about the coalgebra side than the algebra side, I'll talk about these more and kind of forget about these. But you know, there's an analogous story going on for DG categories. So what is a categorical coalgebra? A categorical coalgebra consists of this information right here. So C, delta, D, and H, where C and delta are, that is a graded coalgebra. So notice I did not say differential. It's just a graded coalgebra. What is D? D is a map of degree -1 that does not need to square to 0, right? So if d squared to 0, then this would be a differential graded coalgebra, but we are allowing the differential to not square to 0, right? But we have some term h that we call the curvature, which is going to measure the failure of from d to squaring from squaring to 0, right? So in a very concrete way, d squared is going to be the commutator of h, right? So h is really measuring the failure of d from squaring to 0. So far, it seems like these categorical coalgebras are not great objects in the sense that we just seem to be taking a coalgebra, a DG coalgebra, and ruining the differential. But hopefully, I'll convince you that that's what we want to do for our application at least. Okay, what else do we want? Well, for the connected coalgebra, we wanted one copy of the ground ring at C0, which kind of represented that choice of base point. But now, since we're not choosing a base point, we're going to have many copies of R. So we're going to have this is R module generated on the set-like elements of C. The set-like elements of C are all the elements that for which the co-product acts as the diagonal map. And we think of those as the points that we are allowing in our code. In this case, may. And then lastly, we want the projection map C to C0 to be a chain map. Well, we think of this as a chain complex where it's concentrated at degree 0. And then the point of this is that this is going to give a C0 comodule structure on C, which we'll need for our constructions, but it won't show explicitly today. Okay. So now we're changing our framework from connected coalgebras to categorical coalgebras. But the good news is that our constructions kind of go through. If we have a topological space, we can associate with a categorical coalgebra of singular chains, where this is produced by modifying the usual differential. From singular chains. I'll say something about how that differential is modified in one or two slides later, I think. Okay, so there's a version of the singular chains that gives me a categorical coalgebra. Now I do not have to choose a base point, and I have this theorem again that uses this version of causal duality to have this basically the same statement, but in this categorical setting. So given C a categorical coalgebra, then the co-Hochschild complex on C is quasi-isomorphic to the Hochschild complex of covar C. Remember now covar is this different version of covar that takes categorical coalgebras to DG categories. Of course, these constructions, co-Hochschild and Hochschild, were defined for coalgebras and algebras, but there are versions that work in an analogous way for categorical coalgebras and DG categories. For example, the version for co-Hochschild of a categorical coalgebra uses the co-tensor product instead of the tensor product. And for the differential, we have to add the curvature term for everything to actually to be an honest differential. So I just want to point out that even though for the categorical coalgebra, the differential does not need to square to 0, when we pass to co-Hochschild, we get an honest chain complex, so it does square to 0. Okay. Now from here on, I'm gonna try to give some combinatorial ideas to justify how this is related to the chains on the free loop space, just like the results from the 80s from Jones and Quitwilly did, but now in this new setting of categorical coalgebras. Okay, in order to, yes.
Did I just miss it, or did you not define overline M in the previous slide?
I did not define this. Yes, so that is, yeah, that's my bad. It's because I just, for time reasons, I'm not really describing anything that goes on the algebra side. I can tell you what M is. M is, A is a DG category, right? So all of the morphisms are chain complexes, and then you want to yeah, and then you want to put them all together in one big like module, and that's M basically. You just put them all together.
Cool,
Does that?
thank you.
Yeah. Okay. Yeah, but yeah, this is going to happen throughout. I apologize for that. There are things that I just will not define, unfortunately. Okay, so let's go back to this idea of loops of singular chains and that partial interpretation of that. Well, we are now in the setting of categorical coalgebras, but the underlying R module is still the same. It's still just singular chains. So for our picture here of an element that looks like this, we are arranging it in a circle. And let's say, just for the purposes of this toy example, that C0 has degree 2, C1 and C2 have degree 1 before the shift, and then after the shift, now they have degree 0. Well, then our circle of elements C looks like this. But if we unravel, which I'm not doing here, if we unravel what the cotensor product does here between two elements that are chains, what's saying is that the last vertex of C0 is the first vertex of C1. The last vertex of C1 is the first vertex of C2. The last vertex of C2 is the first vertex of C0, right? So in a sense, they are composable. So really, this picture, we can actually just draw it like this. Where this is C0, this is C1, and this is C2. And then C0 is special, right? So this is marked. And then how do we think about elements in the coaxial complex of the coalgebra of singular chains? Well, we're thinking of elements there as loops of simplices on X, basically. And then you'll hear me probably use the word necklace. So like a necklace on X, closed necklace on X, and I'll probably also use the word beads to refer to the single CIs here. Okay. So if we just look at this picture and we try to imagine, like, if we were to define a differential on this thing, what would we want to capture? If we were to define a differential of this thing, well, one reasonable thing to try to capture is all of the sub necklaces that live inside this necklace, right? So for example, C1 and C0 must always be there, but let's give this numbers so it's easier to visualize. But we would also like to have this one, right? It would also be desirable to have all right, remember we're marking stuff, right? So this one, all of this is marked. Here we can mark the left one. Here we can mark the right one. This is 0, 1, 1, 2. And we have this choice. And then we would have the other choice, right? So that's what we would like to a differential and this type of thing to capture, right? Now, notice that these guys these guys here are terms that would come from applying the co-product on C0. And then the remaining one will come from the usual differential of the singular chains applied to C0. Now, notice that the reason or a reason we would not like to use the usual differential for our simplices here, for our singular chains here, is that we could get, the usual differential would give us an element that looks like this, right? Hopefully I'm making sense. I'm thinking about applying the usual differential of singular chains to this element C0. So I get all the three sides, right? But I see that with this side, I'm going to have problems. With that side, I'm going to have problems because I don't get a subnecklace, but I do want to keep this one, right? So this thing I want to avoid, and then this one I want to avoid. So what is the modification that one has to do to the singular chains functor in order to get a categorical coalgebra? It's exactly that. You take the usual differential and you avoid basically the zero phase, the phase opposite zero, and the last phase opposite last, the last term. And that guarantees that when you pass to coaxial, you're actually capturing what you want to capture with your differential, which is all the sub necklaces of your necklace of simplices on X. So hopefully that made sense somewhat. I'm gonna pause if there's any questions right now on this. All right. Notice that this do we have 5 terms here? So the number 5 will appear later as well. Okay, now I want to relate this coaxial complex to eventually to free loop on X, right? So first we're gonna relate it to paths. And we're gonna use an idea by Adams. So Adams described an idea that assigns to an n simplex on X a n minus 1 family of, or n minus 1 cubical chain on X, right? So from simplices to cubes, and we drop dimension by 1. And the idea is, I think, very nice, very simple. We think of this triangle here, so this 2 simplex on X, we think of it as a family, as a 1 parameter family of paths from 0 to 2. How does it work? Well, we go some units towards 1, and then we start going to 2, right? So we're thinking of, oh, sorry about shaky hand. We're thinking about this triangle as paths like that. So for example, for one choice here of path, that's completely determined by this point in between 0, 1. Let's call it S. Well, that gives me a point here between 0, 1, right? So this 1 cube on the right is parameterizing these maps. So on 0, we have this just the map 0 to 2. And on 1, we're going to have that map that goes this, like that, right? Okay, so how does this idea extend to higher dimensions? Well, the extension is quite natural. I'm gonna first, let's say this 3 simplex, I start at 0, I go S units towards 1, then I go T units towards 2, and then I go straight to 3. And then I think of a 3 simplex as a 2 parameter family of paths from 0 to 3, and then that gives me 2 cube. So in this case, would have something like, say something like that. So a point right here. Right? Okay. So maybe this will make sense. We're going to use this idea for all of the beats that are not the special one. The special one is where the base point is going to leave. You know, it has a marked point. So we're going to do something different for the special one, the special copy. So we're going to use another version of the Adams map. But this version of the Adams map will not give me a path, but a marked path. A marked path is just a path with a choice of point on it. So how does the idea work? Well, I go S units towards 1, then I go towards 2, and then along that path, I am going to choose some point here, right? And let's, I don't know, L. Right? And then that cube is given by those two choices. So maybe this is S. I don't know, S would gonna be vertical. S and L, somewhere here. Okay. So notice that the dimension in terms of paths, the dimension of this simplex is it's going to be itself. So there's no need to shift down. But so that's the special beat. So there's no shift on the special beat. But on the other beats, I get something of one dimension less, which works with a shift on the coaxial complex. That's where the shifts come from in this interpretation. There's one thing we are gonna wanna remember on this map, which is the following. So what do these sides mean? These sides mean this is the triangle here, but the mark point is always on the left. The right side is all the maps here, but the mark point always on the right. Down here, we have this, but the mark point is always, no, this is just this one, right? And then the mark point can be anywhere there. And then up here, we have two choices. Either the mark point is here or it's on the right. Okay, so really when we consider this map, we are going to want to remember this choice here of whether it's on the left side or the right side, and we're going to divide our cube here. So this idea from Adams is not just going to give us cubes, it's going to give us cubes with a given subdivision that is completely determined by the combinatorics of my simplex. Right. Of course, there are more like explicit descriptions in terms of formulas, but I'm trying to give like kind of like an idea from in pictures. Now notice that now we're gonna get a pentagon, right? Because we divided this one face. So we're gonna have 5 sides, which relates to the number 5 that we found before from the differential on the coaxial side. Okay, maybe I will not say this, so forget about this. Forget about this thing for a minute. All right. So this idea of Adams is going to give us a map from the chains, the categorical coalgebra of chains, to cubical chains. But it's not really cubical because they have this subdivision there. So this is the map. So this is the map that we were seeing before. So we have a singular chain, and we're associating to it a subdivided cube of marked paths on X. And then this F stands for freehedra. It turns out that these subdivided cubes have been studied in combinatorics, and they're called freehedra. That's where I'm using F there. Now remember that we have causal duality in the background, and then there's the unit map of that adjunction, that bar-cover adjunction gives us a map down here. Okay. And now there is another map from this object down here to a version of the chains on the marked paths on X. So I'm not going to describe that explicitly because of time reasons, but it's chains on it's chains parameterized by products of simplices and cubes. These cubes are going to come from atoms without the marked path, so the atoms idea. And then these simplices come from a map described by Goodwillie that tells us how to, if we have, you know, that was a picture that didn't explain. We have two composable paths, then that produces a simplex of paths, of marked paths. Okay, so again, I'm not describing this explicitly, but this arises from the work of Goodwillie. It's an explicit map with a formula, literally given by a formula. It's very concrete. Okay. Now, once we see this diagram here, well, of course, we want to fill it out, right? So we would want to find something here, and ideally, would make this thing commute. So in order to do that, well, what do? Let's choose some C0 that lives here and the singular chains. You know, if we apply F, then we get a free so we get this subdivided cube that completely depends just on the dimension of C0. Right? And then we want to compare that to whatever we get under this composition. So under this composition, it turns out that we get another type of polytope that's quite nice. That also only depends on C0. I'm calling these Goodwillie polytopes. And I believe they're interesting in their own right for combinatorial reasons. They have nice combinatorial properties. So I'm going to try to remedy the fact that I'm not giving you a definition for the Goodwillie polytopes by showing you pictures. So hopefully that'll, I don't know, make someone happy. So the F and G polytopes look like this. On degree 0, they are just points. On degree 1, they are, you know, one simplex or a one cube, which is the same. And on degree 2, we have the one that we already saw before. This the 2 freehedra, which is the subdivided square, which is, in other words, a pentagon. And then the G is just going to be this little house, which is also a pentagon. So again, same. And on 3, we do see a difference. We have this cube that is with 2 subdivided faces, and then this kind of like weird cubey object on the bottom right. So how do we get the G polytopes? Well, if we look at an F polytope and we look at the points that we're adding, the subdivisions that we're adding, and we just move them away from the cube, let's say 1 unit or whatever, then, you know, we're going to get the house. That's how we get that. Then we do the same thing for the other subdivisions there. We just push them away from the cube. And we take the convex hull of that, then that's how we get our G polytopes. And this will happen in general. That's one way to describe the G polytopes from the F polytopes. There's other ways that are just kind of like a recipe for knowing which the convex hull of which points will give you the G polytope. Now, I said this kind of backwards because really what we want to think about is that if we project a G polytope into the cube, into the underlying cube, there's always going to be underlying cube, we actually recover the F polytope. So it's a very nice map. This projection map is very nice. It respects the faces, so faces go to faces and so on. So here, for example, we see that this is a kind of like a tetrahedron here. This is going to get collapsed to this edge. And then these sides are going to melt into that side. And that one is going to melt into this side, right? And that's how we get that. G polytopes. Right. So now, what have I said? I'm saying that there is a projection map from Gn to Fn. Right. This should induce some this induces a map, right? Induces a map like that. Whatever. To G. No. Not only that, then G polytopes also have a very nice subdivision into products of simplices and cubes. So for example, this one right here, well, this one is just one simplex. It's also a one cube. And then what is this one? This one has a one cube and two cube and a two simplex, right? And then this one, well, underneath it all, there's a big cube. There are also, I don't know if you can see them here. They're prisms, right? They look kind of like this. There are two of them, two prisms. So what are prisms? They are delta 2 cross delta psi 1. And there's also a pyramid right here, right? There's three simplex here. Okay, so the reason I'm saying that is that I cannot avoid to show this, because in dimension 1 we have one thing here. In dimension 2 we have 1 and 1. In dimension 3 we have 1, 2, and 1. And then you can guess what we will get on higher dimensions. So there is a very clear recipe that's given by Pascal's triangle of how the G polytopes are actually subdivided, which is very nice in my opinion. Okay, so concretely, what does this give us besides pretty pictures? Well, we have a map rho that's induced by the projection map from G to F. And since every G polytope has a subdivision into products of cubes and triangles, we have the map I, right? And then we can think of the composition, and that will give us this arrow down, which is what we wanted. Turns out that this nice diagram is commutative, right? Almost by construction. This is going to be commutative, and all of these maps are quite special. I do want to point out that this is not a map of chain complexes. This is just a map of graded R modules. The reason is that this F is not compatible with the differential of C, because it's compatible with the differential of the Kohashu complex. So it's going to be nice when we kind of like lift it to the Kohashu complex. Okay. All right. So really, this is where I wanted to get, because this diagram induces a diagram on the Kohashu and Hashu level, right? So this we think of this as the special bead. And then what we want is to tie around the other beads. Same as here, we think of this as some special bead and want to tie around the rest of the beads. Again, this is just pictures, really, it's not math. But then we get this theorem, which is given a topological space X, the diagram on the previous slide induces the following commutative diagram of quasi-isomorphism of chain complexes. So it turns out that everything here on this diagram is going to be a quasi-isomorphism. This map alpha comes from that unit of the bar-cobra adjunction, and these maps are of course induced by those polytope maps that come from the ideas of Adams and Goodwillie. Now, in particular, what this gives us is that the Kohashu complex of the categorical coalgebra of singular chains in X is quasi-isomorphic to the singular chains on the free loop space of X. None of these are the singular chains, but after subdivision, you choose a triangulation, then you can land in singular chains and say it like this if you choose to do so. Okay. Now, in a couple of minutes that I maybe have, I'm going to very fast tell you about the equivariant part of the story. So I apologize if it's a bit rushed, but I don't have a lot of time. Okay, so we would want this to remember or encode the circle action on the free loop space of X. So that's what we're going towards. So the free loop space again has an action by rotation of loops. So for example, let's say that what's a good letter? Yeah, let's say the little f is the fundamental pass of S1. Then if I have a chain on the free loop space of X, I can tensor with this class. I'm sorry, this is a representative. So it's a chain, right? It's a representative of the fundamental class of S1. I can tensor with it, and then I get an element here. But then we have the Eilenberg-Silver map that gives me an element in the product of S1 and L of X. But we have a map from this to L of X because we have an S1 action. So here we use the action of S1 on Lx to produce, again, a chain on L of X. So what is this? This is an operator that is going up, is degree plus 1, and it's using the action. So it's encoding the action of S1 into algebra, right? And it's very nice in the sense that it actually squares to 0, and it anti-commutes with the usual differential of the chains on the free loop space. And then algebraic objects that have this structure, so they are chain complexes with an extra differential that goes the other way, and they anti-commute. They have been studied before. They're called mixed complexes. And there are several ways, precisely 8 ways, to compute the homology of a mixed complex. So this is happening on the topological side. On the algebraic side, so on the coaxial complex, we will also have an operator that goes up. This is usually called the cons operator. And again, it's a degree plus 1 chain map that is squares to 0 and is anti-commutes with the coaxial differential. So, and again, it's encoding. So I apologize, I'm not giving you the explicit formula for it, but it encodes the fact that elements in coaxial are arranged in a circle, and I can turn them around. Right? And then I can think of a mixed complex as this big double complex that intertwines the differentials going up. Okay, in this case, I'm using uppercase B, and the differentials going down, I'm using lowercase b. And there's this huge double complex that goes all the way to infinity on both sides. And then depending on which totalization you decide to use, and whether you select subcomplexes or quotients of this big complex, you get different homology theories for a mixed complex. It turns out that for if we use the coaxial complex, all of these versions that we can get in general, which there are 8 in like a priori, they all collapse to just 3. So they're all quasi-isomorphic. So they're all either trivial or quasi-isomorphic to 3 versions, which I'm describing, I'm summarizing in this picture here by just saying that we take the double complex and we take kind of like the positive side, we take all of it, or we take the negative side, and then we totalize and compute homology. And that gives me 3 versions of homology for this mixed complex of coaxial, which we denote by sig plus, sig infinity, and sig negative. Okay, and now the main theorem is that this quasi-isomorphism that we had between coaxial and the chains on the free loop space is compatible with these extra operators that are encoding the circle actions, right? So in particular, we have this correspondence between these 3 versions of homology, right? So on the left, we have positive, periodic, and negative. And on the right, we have the same versions, but for this mixed complex, which have been related or are related to topological object. So the positive is related to homotopy orbits, so the homology of the homotopy orbits. The periodic would be homology of the homotopy Tate fixed points, and the negative is related to the homology of the homotopy fixed points. Okay, and then just in the last maybe 20 seconds, let me just highlight what I want you to take away from this talk. So I introduce a model, and this model has three special things going for it. First is a small model. It uses coalgebras instead of algebras. So why does that make it small? Well, because secretly we're just using this. So most of the algebra models at some point pass to an object that looks like this, and this object is huge, right? This is kind of like a free thing. This is just very, very big. But our model stays here, so it doesn't blow up unnecessarily by restricting to the coalgebra world. We use many points in the sense that we use categorical coalgebras instead of connected coalgebras, so we don't assume a choice of base point. And the last thing, which unfortunately I did not tell you about this today, it has no simple connectivity assumptions. So the input, the space that we can consider can have like any fundamental group that you want. And this is going to work. This is related to the notion of equivalence that we use for the categorical coalgebras, and how it's a stronger notion than quasi-isomorphism, and it's able to tell apart the fundamental group. All right, so I'm going to stop there. Thank you again for your attention. Now I'm going to leave you with a few
Right, thank you so much. Does anybody have any questions or comments for Lenya?
Question. One of the results of that school of Woodville, Jones and company was that the base loop space was related to cyclic homology. How is it coming in your big picture?
Yeah, so that's true. What they do is they think about the base loop space, and that is that's a topological monoid, and then that is related to cobar of the coalgebra of base loops, right? So it's it's funny because it's like you know how you use omega to denote base to denote loops, and you use omega to denote cobar. So the point is that they actually will be interchangeable in that situation. So there is a complete quasi-isomorphism that relates the Hochschild complex that you get from the base loop space, and the Hochschild complex that you get from cobar of the coalgebra of base chains. And that's actually one of the ways that you can prove this result is like by explicitly doing the maps, and then kind of like using Jones' work to say, but Jones already related this to the Hochschild complex on this monoid of base loops. Does that answer the question?
Yeah. Also, I have a question about this sort of equivariant homology of the free loop space. Then you had, you had three byproducts of the pi complex. So it was like cyclic class, if I remember it correctly. Then it was periodic cyclic minus. So what is the upshot about the homology of the equivariant loop space?
Right. So the point would, yeah, I guess the point is understanding the action, and having a homology that takes that into account, right? Like the action by rotation of loops. Those three versions are so at least the one for the positive one can be directly related to the Borel space of the free loop space with respect to the action of S1, right? So it's actually computing the homology, the honest homology of that Borel space, which is the homotopy orbits of it.
Right.
I'm not sure if the other ones compute the homologies of like honest spaces or not. Yeah, but at least the upshot in that sense is that you would get approximately, you are computing the homology of the space of orbits on your space, right?
You're saying it will be one of those complexes, right?
Yeah, one of those does that. Yeah, the positive one does that. Yeah.
Positive? Yes.
Yeah, they are related by I mean, there's a long exact sequence related to the three of them, because since they all come from this big double complex,
Yeah.
and then one is like covering the, just taking the right side, just taking the left side, or all of it, you can actually relate them by on the complex level, you relate them by a short exact sequence, which induces a long exact sequence in homology. So they are related in a way.
Okay, thank you.
Do we have any further questions for Daniel? And let's thank him again. Yeah, Daniel, thank you so much for the talk, and I apologize for the technical issues from my side.
No problem. Thank you very much for the opportunity to speak.
If you wouldn't mind sending us your slides, we'd love to post them on our website if that's okay with you.
Yeah, perfect. I'll gladly send them.
Awesome. All right. Thanks so much.
You're welcome. Bye-bye.
Thank you. Okay.